This is background material for the things that are used in this first lab experiment. You may recall from 302 and 303 lab that we built a filtered full wave rectifier circuit. One we built actually looked something like this. What happens is when the input's positive, current flows in this direction. And when the input's negative, current flows in this direction, always producing a positive voltage. But because we have a load hooked up here, the capacitor begins to discharge and then gets recharged back up again each half cycle. The load in our particular case here is going to be a digital color organ and all the circuitry associated with it. So not a physical resistor, but a set of components and circuit boards that we'll be hooking up. The voltage in here was not the wall outlet, but was a step-down version of it. We used a transformer to do that. What this transformer does is take the input voltage and make it smaller. A thing called the turns ratio. In this case, if the turns ratio was 9, we're taking an input, say, of 170 volts, stepping it down to about 19 volts. We also had options with a center tap. This can be used to actually eliminate 2 of the 4 diodes and still get full wave rectification. This part of the experiment is using voltage regulators to create different voltages to run different parts of our digital color organ. The notes that follow here are taking a look at some of the same parameters with a very different type of regulator. We're talking about an LM117, and we're not going to be using this specific regulator in the project and will not modify one to put it in. But the ideas of this voltage regulator are the ideas of almost any voltage regulator's datasheet. So I'm going to use this as a way to introduce ideas, but have you look at specifics of the datasheets and to think about how those circuits are designed and how the components were picked. The idea of a basic regulator is like examples that we had done in the 302 course in the 303 lab. This is an integrated circuit that has an input that may be varying in value, but the output is constant, or fairly constant. In this particular type of a regulator, the output voltage is a reference 1.25 volts. The voltage that's here needs to be bigger than this voltage at every instant in time by at least some factor, and this is called the dropout voltage. In other words, when this is bigger than the dropout voltage plus the reference voltage here, then we have a voltage across here that's greater than 0. And we need this to operate the transistors that are inside this integrated circuit. The LM117 can also be used as an adjustable regulator. In other words, you can pick different values of output voltage. And the trick here is to put a resistor from here back to ground. So what I've got is a voltage across here. It's like a Zener diode. It's forcing a constant 1.25 volts across this resistor R1. So the current that flows in here then would be 1.25 volts divided by R1. But that current goes into here, and there's very little current coming from here. So the voltage across here then is that current times R2. If you factor this out, what you get is the reference voltage then times a scale factor. But again, this is a piece of silicon, so I have to make sure that the voltage here is big enough. And that has to be the voltage here plus whatever it takes to operate the regulator. So we always have to have some voltage across here. It's really just a series of transistors. We've got to keep them in their active regions. So the voltage here needs to be bigger than the output voltage, whatever you've adjusted it to, plus what's called the dropout voltage. And I'll explain this in the upcoming slide. Let's put some numbers in here. If you had a 240 ohm resistor for R1 and a 5K for the pot, then when you adjusted the pot from 0 ohms to 5K, we would have an output voltage of 1.25 to 27.29. Again, the voltage here needs to be bigger than this number by this value plus whatever the dropout voltage is. We're looking at different kinds of regulators in our project, and you'll see that these data sheets also talk about some of the same parameters. But we're not going to use this type of a configuration with the regulators in the digital color organ project. We're looking at a variety of analog integrated circuits in our digital color organ project, one of which in this case is a voltage regulator. This LM117 regulator has a thing called a macro model, and you'll find that op amps and other types of linear integrated circuits, and even some digital ones, if you search the web and search companies' websites, have things called macro models. These are actually not the transistor level model of the integrated circuit, but an equivalent circuit of what's inside the IC. It's using the parts of SPICE to mimic the behavior of the IC. We say, well, why do this since you know the schematic of what's inside there if you're manufacturing it? Well, a couple things. One, the manufacturer doesn't want to reveal the techniques that they've used to make their products. And secondly, the circuits are very, very large, and it's sometimes very difficult to get convergence. So when you run a simulation, you may find that it just doesn't converge to an answer. So the macro model is a much simpler circuit. It takes some of the circuitry that's inside the IC and mimics it. For the voltage regulators, there's usually a thing called a pass transistor that essentially is giving us the regulation like we did in some examples in ECE 302. This is a model that I actually developed for the LM117 HV many years ago, but I could show you what the idea of a macro model is. So here's all of the description of what this particular IC does in terms of a series of components that are the parts that are in SPICE. You can find this model on the ECE 402 homepage, on my homepage, under SPICE models, if you wanted to run this particular macro model. But you'll find other ones on the web that deal with the parts that we're dealing with in the project. You don't have to do a simulation, but if you're trying to figure out something, it's a way to quickly see what's going on before you have to go to lab and measure it. One of the parameters that's very important in a voltage regulator is its ability to reject any of the ripple that's associated with the power supply. In this configuration, I'm testing putting a capacitor across this resistor R2. And if you find this picture in the LM117 datasheet. But again, we're not going to be using this particular regulator in the project. And you can see here that in this graph that putting a capacitor across R2 has an effect on the results. Now, ripple rejection is really the ratio of the output to the input reciprocal. The AC signal is always being stepped down when going through a regulator. But most engineers don't like negative numbers, especially in dB, so they flip it over. So it's actually a plot of the voltage gain reciprocal, which would be the attenuation. But they call it ripple rejection and kind of get rid of the minus sign that way. And you can see adding this capacitor makes the signal get smaller and smaller compared to the case where you don't put the capacitor in. And then at high frequencies, the value here is 2.12 dB. Now if you convert that to regular units, that's about 1.276. So if there's a 1 volt ripple at, say, a couple megahertz, then what's appearing at the output is that value of 1 divided by 1.276. So almost all the signals coming through at higher frequencies. The thing we're most concerned at is 120 hertz because that's the frequency of the full wave rectification. So this does quite well at those frequencies, but eventually no matter what you put in with these capacitors there, you're still passing some of the noise at higher frequencies. So if we got some interference on the power supply line due to high frequency pulse or maybe someone's cell phone transmitting, that's just going to come right through the voltage regulator. So that's an important parameter in dealing with voltage regulators. Another one is a thing called the dropout voltage. We talked about that a few slides back. This is a plot with the SPICE simulation using this macro model of the output voltage here as we vary the voltage here. So what's on the x-axis here is the voltage across the regulator. That's the voltage from here to here, okay, as a function of the voltage at node 2. That's on this axis here. So you can see the regulator is producing an output voltage of about 9.562. At the bottom of this page you can see the calculation, see how close that is. And the dropout voltage is defined as when the output voltage drops by 100 millivolts. So what's happening is the input voltage is being varied from 10 to 15 volts. And here's the value when you're at 15 volts, but as you're lowering this to 10 volts, you're seeing that the output voltage eventually is going to start to drop. And when it drops by 100 millivolts, that's called the dropout voltage. In other words, things are starting to change here where I'm not getting the regulation anymore because this isn't big enough. And then the dropout voltage is the voltage across the regulator when that's occurring. So what that's really telling you is that you need to have at least 2.1854 volts bigger than the output. And if you were to calculate using that previous formula, you'd see that we would predict about 9.559. Another important regulator parameter is called line transient response. This is what happens to the regulator if there's a change in the input voltage. So you might get a spike of something because you've put a load onto the circuit. With digital circuits, we've got pulses all the time, and so it's pulling currents with a variety of frequencies, and so we get spikes on the power supply line coming out of that wall wart. Here's a case of applying a voltage of about 1 volt on top of the voltage that's here. And what's happening at the regulator is that the regulator will eventually regulate, but you'll see a response due to that jump in voltage. So what we've got here is a step function, and we're getting what looks like a second order resonant circuit kind of ringing out. Now our regulator is not giving us a solid voltage, but actually a changing voltage. And this can affect our circuitry in the analog and digital sense. One way to suppress this is to put capacitors across some of the components. In this case, putting one across this resistor R2 and one across the load. So in this simulation, I've included the losses of the capacitor, and I'll talk a little bit about this at the end of this lab lecture. You can see what happens to the response in the time domain. I've kind of blown the scale up a little bit here. So here's our previous case. It just made it a little bit larger, but when you put these capacitors across this resistor and across the load, you can see that you see a great deal of attenuation because it's holding the value of the output voltage a little bit more constant. Now in our lab experiment, we're going to be using capacitors here, and I've included the resistive losses of this capacitor. And the reason is that this is a feedback circuit and it can actually go unstable, and that's really what we're seeing here. We're seeing parts of an instability that's just a little bit in the left half plane. And the lossiness of this capacitor actually helps things out. You'll see that in our project that the author uses these types of capacitors at different points in our voltage regulators. Another important parameter in voltage regulators is a thing called load transient response. If the load changes abruptly, the voltage here also has some effect. So again, we're not regulating as solid as we would like to be. So what I've got here is I'm putting a voltage source and just changing its value to draw more current or less current. What's happening is I'm getting a step of current of about half an amp. And you can see that the output voltage of the regulator now, again, is supposed to be over here, but we get this dip associated with that, and it recovers from the changes that are there. Again, this changes the value of my reference voltage, and this can affect my analog and digital circuitry. We're going to look at measuring these things in our digital color organ, and then we'll decide whether we need to make changes to our circuit or to leave things alone. Okay, if you put capacitors across some of the components, again, we're not going to be using a resistor like this, but really a capacitor across here, you can see the effect of putting that capacitor there. And again, the losses that are here are important to model because in lab, these are really here, and they do have an effect. So here I've again blown up the pictures a little bit. You can see without these capacitors, this response due to this change in current, but by adding those capacitors, we can smooth that out. And again, this can sometimes cause problems in our circuit because we're letting our voltage change when we're trying to have a nice solid value as we're applying this to our analog and digital circuitry. Let's take a look at non-ideal capacitors. Here's a plot of the magnitude of the impedance of the capacitor versus frequency. In this particular case, it's an electrolytic capacitor. Now, as frequency goes up, we expect the impedance to go down, and it's indeed doing that, but then all of a sudden it goes back up again. If you recall from 202, this was the curve that we had for a series resonant circuit. So we're going to actually model it this way. When the frequency is low enough, we've got what looks like an ideal capacitance. We're going to model the capacitor just that way. Okay. Then as we hit the resonant point, the impedance of this series line inductance, which is associated with the wires coming in here, cancels the impedance of the capacitor, and we're left with just, in this case, a real part of some value of resistance. It's called the effective series resistance. And as frequency increases, this is looking more and more like a short circuit, and we're starting to see this approach more of an open circuit. So the problem with this type of capacitor is it's very good for large value of capacitances, but really for low frequencies, for things in the line voltage frequency range of 60 hertz, 120 hertz. But as we get higher with spikes and pulses, it's just going to let those signals pass through. Now in our labs, we've used other types of capacitors, and one was a polyester film capacitor. It too has a curve like this, but the resonant frequency is much, much greater than 1 megahertz. So you'll see in a lot of designs that people put a capacitor in parallel with an electrolytic capacitor. And what this is saying is that at low frequencies, this is going to take care of our circuit and keep things fairly constant because the voltage across here can't change instantaneously. But as frequency goes up, this looks more like an open circuit than a short circuit. We'll put another capacitor here to basically short out the leads of this capacitance as the frequency goes up. And so we don't have this case occurring now. We just have something in parallel with it that's going to short out the capacitor. So we want to attenuate those high frequency pulses. Don't let them pass through our circuit. And again, that's what the regulator was showing, that as the frequency goes up, we're basically passing any noise that's put onto the power lines. Now, this isn't going to give you all the answers to your attempt to improve this digital color organ, but it gives you the background that you need to do this. And this is our lab number 1, the power supply designed for the digital color organ.